Asymmetric encryption powers the world today. It's really useful. Without it, we couldn't do online banking. We couldn't do a lot of modern stuff. It's really powerful. It's different than symmetric encryption. With symmetric encryption, the same key is used to encrypt something, and the same key, we use that exact same key to decrypt something, both ways. Asymmetric encryption is different. We use two keys, so it's also called public key, private key cryptography. With public key, private key cryptography, we encrypt data with one key and we encrypt data with one key and decrypt data with a different key. So I might encrypt data with a public key. The only person that can decrypt that data is the person with the private key. Sounds kind of crazy. It's not very intuitive. It's very different than the door lock to your home. To your home, you just use that same key to lock and unlock your door. That's fine. But with asymmetric encryption, you would use one key to lock your door and you'd use a different key to unlock your door. Really powerful. It's used primarily for two things. One, signing files. So if I've got a private key, I don't give that private key to anybody, but I can sign a file with that private key. Not like drawing a picture of my signature, but digitally signing that file. And then I'm going to give everybody my public key. The public key can be distributed. It's supposed to be given away. For it to be useful, it has to be given away. So if I sign something with my private key, anybody with my public key can verify that yes, indeed, that file was electronically signed by me with my private key. Asymmetric encryption is also used for distributing temporary symmetric keys. We'll talk about that later with HTTPS. We'll take a look at how this works with the GNU Privacy Guard. There are different algorithms supported by the GNU Privacy Guard. We're going to use the RSA crypto system. Everyone just calls it RSA. R, S, and A just come after the last names of the people who developed this system. It's a system because there's a lot of things under the covers, how keys are created, how it's used, all that kind of stuff. To simplify things a little bit, the public key and the private keys are just big numbers. So imagine this is all just one big number separated by commas. It's a very, very big number. That could be my public key. And my private key, which I don't give to anybody else, could look something like that. Very huge, big number. Not really guessable. If somebody wanted to try to brute force this, they would have to be computing this for a very long time. These keys are linked, so the public key can be derived from the private key. They're linked together, so I can't just use a random public key with a random private key. These are key pairs. When you create a key pair, you'll create both the private key and the associated public key. Slightly more complicated than that, but at a high level, that's what we're doing. Now, these keys are somewhat computationally expensive to create. On some systems, just depending on a number of factors, when you create a key, your system might churn for a little bit, trying to build up some entropy, some random data, to make sure that your key is random, unique, and secure. Typically, these keys are long-lived. You might use the same key for a year or two, so you're not creating these all the time. If you're using that same key for a long time, if your private key got leaked, well, then anything that you did with that private key would be suspect. So this does not provide perfect forward secrecy, PFS. It's a big deal. We don't want somebody to, for example, capture all of our web traffic, and then after a year or two, their private key gets leaked, and then all that captured web traffic can be decrypted using that private key. So it's good, it's used, there's a lot of good ways to use it, but there's no perfect algorithm that solves every single problem. When I was working in industry, my boss came to my office one day. My boss said, "Hey, Jim, I want you to automate payments from our accounting system. I want you to send those payments to Bank of America. Bank of America needs you to electronically sign these files using RSA. And I was like, great, I don't know what you're talking about. And so I did some research. I used a tool called PGP, Pretty Good Privacy. It was a proprietary tool that at the time at least was owned by PGP Corporation. But the PGP standard is open. So the GNU Privacy Guard is a free implementation of that public standard. We had to use the paid version just because we felt like we needed support. If something went wrong, we wanted to be able to call somebody on the telephone. And occasionally I did have to call those people on the telephone to ask them about certain issues that we were having with compatibility with other systems. But the GNU Privacy Guard will do the same thing that in this exercise, we'll be doing the same thing that I was basically doing, creating files to send to a bank. The bank wanted to make sure that any payment instructions we sent them actually came from us. So let's walk through that process. Let's make sure we're in Linux, we're in our home directory. pwd, print our working directory. I am in Ubuntu. So I'll run GPG --full -generate -key. This is going to walk us through a wizard basically and ask us some options. What kind of key do we want? We're going to use RSA and RSA. Just ignore everything else for now. All that's fine. Just know that this does support other algorithms. ECC is probably one of the most common emerging algorithms that's becoming more adopted. That's elliptic curve cryptography, but we'll just take a look at RSA for now. I'm going to choose one. I want RSA and RSA. How big do I want it to be? I'll choose 3072. It's a pretty big key, to be honest. One downside with RSA is that to give you good security, the keys have to be pretty big. I'm going to say this key is not going to expire. Maybe not ideal if I were using this for banking transactions. If I was generating this for the bank, I might say 13 months. I might use it for a year, then give myself a month of buffer in case there's any issues updating the key. But for here, I'm going to say 0. It does not expire. So it's warning me. It's like, yeah, you sure about that? Are you sure? Yeah. Yeah, I'm sure. My real name. Donald Duck. Is that my real name? No, in fact, it is not. You know it's not my real name. What is my email address? It's donald@duck.com. Is that my email address? No, in fact, it's not. Just be aware, anybody can put anything in here, so how do we trust it? That's something I'll let you think about. Comment. I'm not going to have any comments. Yep, that is O for OK. Now, passphrase. I'm going to give it super terrible passphrase called password. Yeah, take it. Just do it. Password. We need to generate a lot of random bytes. It's a good idea to move your mouse, do all that kind of stuff. Okay, it generated it. Sometimes this process can take several minutes. Just depends on a lot of factors on your system, but this was pretty fast, so that's nice. I've got my key. So I can see I've got, it says public and secret key, created and signed. Fantastic. It put it on my key ring. It tells me where it stored it. We don't have to worry about that. It'll find it for us. I can see the public key. So I created it using the RSA algorithm, 3072 bits. All that's good. I've got a fingerprint here. This is something when I created a key and I had to send it to the bank, I said, hey bank, here's my public key. Also, here's the fingerprint. So when they load my public key, they can check that fingerprint to make sure they got the right key. So all this is good. If we want to export our public key, like if I just run ls here, I don't have any keys exported here. I'm going to go ahead and run that command GPG. I will -- output. What do I want to output? I want to output it to public.key. I could name it whatever I want. I'm going to say armor. That's going to make it readable text. And then I have to tell it which key do I want. Export. And I called it donald@duck.com. donald@duck.com. So the GNU privacy guard is going to go look on the key ring and it's going to find the key associated with that email address. And of course I misspelled output, so that's fun. I'll add the T there. It's important. No news is good news, hopefully. Let's run ls. I do have a public key there. So if I cat my public key, there it is. I see the end of it there, but I'll scroll up. It says the end PGP public key block. I'll scroll up. Yeah, all this data, that is the key. So if I send this file to somebody, people have got my public key. So this isn't a secret. I can send this to anybody I want. In fact, for this to be useful, I would want to publish this public key. So all that's good. Now, for funsies, we're going to export our private key. We're not going to want to send that to anybody, but let's say we wanted to make a backup of our private keys. Let's do that now. GPG -- output. I got my T in there, so that's good. Private.key, that's the name that I want to output this to. I'm going to armor it so it's text readable. And I will -- export -secret -key donald@duck.com. Passphrase, yeah, thanks for the security. Password. Took a second, but hey, there we are. So now if I list, I've got my public key and my private key there. I'll cat the private.key. And it's going to look similar to my public key. It just says end PGP private key block. So by showing you this is no longer secure. I would not want to actually use this key for anything sensitive because I've just shown all of you what my private key is, which would defeat all of the security. So technically you could steal my key, you could sign files with my key, and people would think it came from me. All right, so we've got our keys on our key ring. We're ready to go. We're going to create something that we're going to sign. So I'm going to touch message.txt. I'll list my file. So I've got my two keys and I've got message.txt nano. So put in your controversial opinion. Or here I might put my banking instruction. Hey bank, send $1 million to Jim. So I'm going to Control O. Oh, it says new buffer. Did I screw up my nano command? I'll call it message.txt. It'll overwrite. Yes, overwrite it because I must have done something wrong. I'm going to Control X to exit. Yeah, I just ran nano. I forgot to say nano. Message.txt. No worries. It's all fixable. Don't worry about making mistakes. I'll cat message.txt just to show. There's my banking instructions. Now I'm going to clear sign this file. So I'm going to electronically sign it with my private key. And by clear signing it, I'm going to keep the text readable. When I was sending data to the bank, this is what I had to do. So I'll say GPG -- clear sign message.txt. I've only got one key, so it knows what I want to use. To use it, it wants me to enter my passphrase, which is the terrible passphrase, password. No news is good news. Let's list those files. Now I've got a new file, message.txt.asc. So ASC is for ASCII, meaning text readable. Let's take a look at that file. I'm going to cat message. I'm going to hit tab. That's not the file I want yet, but there's two files that start with message.txt. I'm going to put .a and hit tab, and it'll fill in the rest for me. Let's see what this looks like. Here's the whole contents of my file. It says begin PGP, signed message. We've got a hash. We can ignore that. That's just helping to verify that all the bits got transferred correctly. Here's the contents of my message. We can read it because it was clear signed. Send $1 million to Jim. And then we've got the signature. So if somebody's got my public key, they can verify this file. They can say, oh yeah, this was actually generated by Donald at Duck using Donald Duck's private key. So in practice in industry, I would take this file then and I would send it to the bank would load it, they would verify the file signature. And once they verified the file signature, they said, hey, we know it came from who it says it came from. So they're going to go ahead and process those payment instructions in that file. This project was complicated to some degree because I had to write all the code to automate this process. I wasn't at the keyboard typing every day. I had to write services that ran on a server 24/7, generating these files, signing these files, generating passphrases, automating all that stuff. Fun project, a little bit stressful, but hey, it was good. We can encrypt data using the public key. So if I want to send you a file that only you can decrypt, you would send me your public key. I would encrypt data using that public key. But the people who also have that public key, they could not decrypt it. Only you with the private key could decrypt this data. So we're going to encrypt this now. We're going to encrypt this same message. We'll use GPG --encrypt. We'll supply the name, the recipient. Who's supposed to receive this? Bugs. Sorry, I only have one public key. It's donald@duck.com. I haven't loaded anybody else's private keys. So for donaldduck.com, I'm going to encrypt message.txt. Notice I didn't say -- symmetric. So by default, it's going to be using asymmetric cryptography here. Checking, all that's good. Those messages, all that's fine. So if I ls, let's take a look at what exists now. I've got a new file here, message.txt.gpg. So I'll go ahead and throw that message out there. Cat message.txt.gpg. And it just looks like a bunch of nonsense because it's encrypted binary data. It's not clear. We didn't clear encrypt something. We didn't ASCII armor anything. So now at this point, only Donald at Duck's private key could decrypt that message. So very effective for encryption purposes. Typically, you're not going to, this can be effective. This can work just fine. It's, instead of sending a file very frequently, this asymmetric encryption is used to transmit a temporary encryption key. So if I've got a large amount of data to encrypt, I might encrypt that with a symmetric key. But if I need you to decrypt that data, you need the key. So I would use asymmetric encryption to encrypt the symmetric key, send that to you. You would decrypt the symmetric key and then decrypt the file using symmetric encryption. So public key, private key cryptography is used in conjunction with symmetric cryptography all the time. All right, so we put a bunch of files here in this directory. Let's delete them. Let's clean up. I can rm m star, that will delete message.txt, message.txt.asc, and message.txt.gpg. Boom, gone. ls, list them. I've got two more files. Both of them begin with the letter P, so I'll rm p star, and that will get rid of those two files as well. Do I still have those keys on my computer? Yeah, I still have my keys on my key ring. I just deleted the exported versions of those keys. If I really wanted to delete those keys from my key ring, I could do so with the following commands. So gpg delete secret keys donald@duck.com. Do I really want to delete it from the key ring? So yeah, I do. This just points out, just because I deleted public.key and private.key, those keys still existed on my computer, just in the GNU Privacy Guard's directory that it created and manages for me. Sure, delete it. It's like, do you really want to delete it? I sure do. Like, do you really want to delete it? This is a big deal, because if you accidentally delete your private key, like, it's gone. And yeah, lots of confirmations there, because that's kind of a big deal. So gpg delete keys donald@duck.com. So this is the public key. The previous command deleted the private key, and I'm going to delete the public key. Yes. So now I've got no keys, so I'm kind of back to where I was. Notice there's fewer confirmations for deleting that public key. So key management is a big deal. How do we protect those private keys? If people had access to my server, they could get access to those keys, and I don't want that to happen. So managing those keys in a secure way becomes really important. One question to think about, I pretended that I was Donald Duck in this example, but I'm actually not Donald Duck. So how do we actually trust that the key, the public key that somebody sent us, is actually associated with the person who claims that identity? That's kind of a tricky problem. I'll let you chew on that one for a little bit instead of giving you the answer. There's a few ways that people have attempted to solve that problem. If you want to go dig into it, I'd encourage you to search out some of the ways that people have tried to solve that problem. But in this example, we use the GNU Privacy Guard to create a public key, private key pair. We signed a file, we encrypted a file. This is the exact kind of stuff that I did in industry in order to securely send data to third parties outside of our organization in a way that they could cryptographically confirm that that file came from our organization.